Hello everybody, my name is Calvin with student ID number of 22055311040. I'm currently studying mechanical engineering in Udayana University. In this video, I'm going to present my presentation about ceramic materials that were made for the assessment of knowledge of engineering materials subject lectured by Professor Dr. Tjokorda Tirta, Nindhia, STMT. All the materials that were used in this presentation were taken directly from this book entitled Science of Engineering Materials, Volume 2 by Menes Chanda. The content that will be discussed in this presentation is introductions of ceramics, structure of silicates, refractories, glasses, glass-like coatings, ceramic coatings, cement, and concrete. Introduction. Ceramic may be defined as inorganic, non-metallic materials that are made and are used at high temperatures. In terms of chemical constitution, a ceramic may be essentially defined as a combination of one or more metals or semi-metals such as silicon with a non-metallic element, usually oxygen. The main characteristic of ceramic is hardness, brittleness, and strength, high melting point, poor heat and electric conductivity, and good resistance to attack by most chemicals, particularly oxygen. Silicates are by far the most important of the silicon compounds, and all of them are based on the entire glass, ceramic, and cement industries. In the following is presented a brief survey of mineral silicates outlining the more important structural silicates. Three main types of structures of discrete anions in which are: first type is discrete anions in which either the SeO4 or silicate tetrahedra are present individually or a limited number of them are combined in ionic groups. The second type is extended anions in which the silicate SeO4 tetrahedra are linked into the chains of an indefinite length or sheets of indefinite area. The last is three-dimensional networks formed by the complete linkage of the SeO4 tetrahedra in all three directions. Three main types of discrete anions are individual SeO4 tetrahedra present, simple silicate ion in which central silicon atom or ion is surrounded tetrahedrali by four oxygen atoms or ions. In fact, the SeO4 tetrahedron constitutes the basic structural unit in all silicates and may be variously represented according to convenience as shown in figure A, B, and C. The first representation is the diagrammatic planar projection. The second is self-explanatory, while the third is tetrahedron as viewed from above, with the central silicon designated as a dot. Next type is two SeO4 tetrahedra share one corner between them. The sharing of one oxygen atom by two silicon atoms while retaining the tetrahedral configuration of each results in the formation of the discrete Si2O7 with charge of -6 is shown in the figure D and E. Last type is each SiO4 tetrahedron shares two corners with adjacent tetrahedra. The sharing of three oxygens by three silicon atoms results in the formation of the discrete ion Si3O9 with same charge -6. Having a ring structure is shown in the alternative representation in figure F and G. Similarly, a cyclic arrangement of 6 tetrahedra will give the discrete anion Si6O18 is shown in the figure H and I. Next is extended anions. Three main types of extended anions are: first, Each SiO4 tetrahedron shares 2 corners with adjacent tetrahedron. The linkage of this type involving indefinite number of SiO4 tetrahedra leads to chain formation of the composition SiO3, or called metasilicate, is shown in this figure. This structure figure on the top. This structure is characteristic of the group of minerals known as pyroxenes. Alternate SiO4 tetrahedra are share 2 and 3 corners with adjacent tetrahedra. Extended anions comprising double chains formed by this type of linkages have the composition Si4O11, or so-called metatetrasilicate, is shown in this figure on the top right. This structure is characteristic of the materials known as amphiboles. Thus, in contrast to pyroxenes, the anionic frameworks of amphibole minerals are built of double chains. Last type is each SiO4 tetrahedron shares 3 corners with adjacent tetrahedra in one plane. This type of linkages leads to the formation of the extended sheet of linked tetrahedra with the ionic composition Si2O5, as indicated by the arrangement shown in this figure on the bottom right. Okay, the last is 3-dimensional networks. Each SiO4 tetrahedron shares 4 corners with adjacent tetrahedron. The sharing of each oxygen atom at the corner of every SiO4 tetrahedron results in 3-dimensional lattices of silicon dioxide. Since in these structures the silicon-oxygen bonding extends in all directions, this material is harder than most minerals which have layer structures, but are not as hard as silica since the latter's surface structure. Next one, we discuss refractories. Refractories are non-metallic materials of construction capable of withstanding high temperatures without appreciable deformation under surface conditions. This property is called refractoriness and is generally measured by the softening or melting point of the material. A common method of determining the fusion point is by comparing the bending characteristic of a small cone of the material with those of a series standard pyrometric cones when they are all heated in the same furnace. The result is reported as a pyrometric cone equivalent, or so-called PCE, of the refractory, which is the simple number of the cone that most nearly corresponds to the test cone in a furnace at the time of softening. Application of refractories. In selecting refractories for particular applications, several other properties such as dimensional stability, resistance to spalling, and resistance to different types of slag also need to be considered. Dimensional stability defines the resistance of the materials to any volume changes which may occur on prolonged exposure to high temperature. Dimensional changes of a refractory brick can be either reversible or permanent, irreversible. Reversible changes are directly related to the coefficient of thermal expansion, while irreversible changes occur due to phase transformations resulting either in contraction or expansion. Spalling refers to cracking, splitting, or flaking of the materials when subjected to sudden temperature changes, also called thermal shock. A refractory may spall in a variety of ways owing to one or a combination of causes, including temperature gradients in the brick due to uneven heating or cooling, which set up stresses of such magnitude as to cause failure. Compression due to volume expansion as of a whole structure of refractories from a rise of temperature sufficient to cause shear failures. Difference in coefficient of thermal expansion between surface layer and the body of the brick brought by surface conditions great enough to cause breaking off of pieces. Slag and metal resistance. It is essential that refractories should not react at high surface temperatures with the substances they will be in contact with them. Next, glasses. Glass has been defined in several ways. The two features which are commonly mentioned are: first, glass is formed from a highly viscous superliquid, and two, the liquids forming glasses possess a structural network of short-range order. Glasses are thus essentially amorphous solids having two characteristic structural features. First is short-range or first neighbor order, and two, a continuous framework of strong primary bonds. To hold the formation of an oxide glass, four simple rules must be obeyed. Considering an oxide AX OY, in this case BY, these rules may be stated as follows. An oxygen atom should be coordinated with not more than 2 A atoms. This rule singles out those oxides which develop network structures. The coordination number of A, in other words the number of oxygen atoms surrounding each A atom, must be small, 4 or less. This singles out those oxides with stronger bonds. The third rule is the polyhedral of the groups of oxygen atoms around A atoms share corners only and not edges or faces. Three or more corners of each isolated polyhedron should be shared. This rule ensures development of a network structure. Relatively few oxides meet all these requirements. It is impossible for oxides A2O or AO, where A is a metal atom, to do so because they lack adequate number of oxygens to form a network. The A2O3 oxides can form a network only if the A atom is small enough to permit triangular oxygen polyhedron. The unusual characteristic of glass, namely its chemical stability, inherent transparency, hardness and brittleness, and its poor conductivity to heat and electricity, are the consequences of its decomposition. The existence of strong covalent bonds between the atoms and the lack of crystal structure. Glass is immune to oxidation attack because it is fully oxidized. The basis for the transparency of glass is its lack of free electrons, unlike metals, and its homogeneous internal structure, typical of liquids. The lack of free electrons severely restricts the absorption of light energy, while the absence of Coulomb boundaries, unlike the in polycrystalline materials, rules out loss of light by reflection inside the material. Since glass has no crystal structure and the atoms are bonded by strong covalent bonds, the phenomenon of slip cannot take place, and glass exhibits a very high compressive strength. Potentially, the tensile strength of glass should also be very high, though in actual practice, the strength is only a hundredth to a thousandth of the theoretical strength, and glass is brittle. These sources of strength, as experiments have shown conclusively, are primarily due to microcracks, tiny imperfections in the structure, which are present in any glass article, no matter how carefully it is made. and which can be augmented by abrasion during handling. These minute cracks or imperfections in glass act as stress razors, permitting stress concentration to localize and exceed the bond strength between atoms to produce bond rupture. However, unlike tensile stresses, compressive stress can be transmitted across existing cracks without stress concentrations. As a result, glass is stronger in compression than in tension. And this is true for brittle materials in general, like all brittle materials. Next is glass processing. Glass is manufactured by melting suitable materials in the required proportion in a glass tank furnace or in a refractory pot, and fabricating the molten glass into desired products. Close attention is paid to the viscosity of the product in the processing steps of melting and fabrication. Viscosity values suitable for the processing steps are shown in this figure. In the melting range, the viscosity of the product must be sufficiently low so that the gas bubbles can escape and homogenization can occur. The working range of viscosities is rather broad. Since different types of operations require different viscosities, thus fast operations such as production of light bulbs require a relatively fluid glass, whereas the drawing operation on a heavy glass sheet requires a viscous product. Four most important uses of glass are the packaging, building, engineering, and electrical industries. The property that makes glass an ideal material for packaging is its chemical stability. Glass in almost every imaginable form is used in enriching buildings. While much of the glass used in modern building is in the form of flat glass, there are many other ways in which glass finds effective use in buildings. Much of the more recent development in glass technology such as laminated and toughened safety glass, wire glass, curved safety glass, fiberglass insulation, and glass fiber reinforced plastics have resulted from the demands from the engineering industries. Glass and many special products derived from it are used in and with electric gadgets and lighting, power transmission, communications, and electronics, etc. etc. In fact, without glass, many applications of electricity would be impossible. The last two other applications of glass that is worth mention is in making domestic and scientific glass. Glass-like coatings. Glass-like or vitreous coatings are widely used to protect ceramic bodies and metallic surfaces. Ceramic glaze. A ceramic glaze is a mixture of materials, usually oxides, which when heated form a permanently hard layer of glass over a ceramic article. Vitreous anomalies or glass lining. Vitreous anomalies are glass-like protective coatings which are fired onto metal to provide resistance against oxidation and attack by corrosive environments. Porcelain anomalies. These are features or glass-like coatings of relatively low thicknesses widely used to protect metallic surfaces. Ceramic coatings are similar in nature to enamel coatings, but they are characterized by much higher manufacturing risks and so are used in applications where high temperatures are encountered. Next is cement and concrete. A wide variety of ceramic cementitious materials are used for different purposes. They have the characteristic properties of setting and hardening when mixed to a paste with water, and so can be used for binding together aggregates such as sand and crushed stone into a coherent solid mass. Or concrete is a building material obtained by mixing cement, a fine aggregate, for example sand, and coarse aggregate, for example crushed stone and or gravel. A water in a suitable proportion so that a plastic and workable mesh results. The product is heterogeneous material in which the particles of the coarse aggregate are embedded in the matrix of water, which itself consists of sand grains embedded in the matrix of cement water paste.